Thank you. So let me first start by thanking the organizers. So this work is somewhat related to the KPZ problem, so I think it's fitting to present it here. It's done in collaboration with Pablo Minini and one of his ex-students, Patricio Di Leoni, and with Raul, who is here, and two people from Chile, Enrique Chiarapegui and Carlos Cartes. And the last part is a work in progress. Okay, so here is the plan of my talk. As I'm gonna introduce some notions that are maybe not familiar to the audience, I will spend some time to explain what Galerkin-truncated systems are and what is their role in fluid mechanics. Just note that they've been introduced quite a long time ago by T.D. Lee. Okay, and I will give specific examples of these systems in the case of a three-dimensional Euler equation and 1D burgers. And then I will switch to the main part of my talk, which is the description of the 1D Galerkin-truncated Burger equation, which is part of this system, but with added viscosity, I mean dissipation term, and noise, such that they equilibrate. And this system in some regime is equivalent to the KPZ system. So then what I will go on showing is that there is, as in the KPZ system, some crossover between the linear Edward-Wilkinson scaling to the KPZ scaling. But I will show that there is a third scaling that is recovered when the dissipation is decreased to 0, and this recovered regime corresponds to the one present in these general systems. So that's the idea of the talk. Okay, so what are these classical truncated systems? Here is the first page of the original paper, 52 by T.D. Lee. So note that he introduced it about hydrodynamics and magnetohydrodynamics, and that here, if you have very good eyes, you can see that there is a spectrum that is like k to the 2, because he was considering 3D examples. So, what are we talking about? So the basic idea is that you start from some given partial differential equation, one that is time reversible, and what you will do is you will seek, periodic solution of this partial differential equation. So if you are numerically inclined, how do you do that typically? You expand everything in Fourier series, and if you do it in a numerical framework, obviously this Fourier expansion cannot go to infinity. It's stopped at some point, which is called the resolution or the maximum wave number you have. So as a practical matter, every time you do a numerical simulation, you have this maximum wave number. So here the idea is that if you fix this maximum wave number to a given value, then you've changed your PED, you've morphed your PED from a PDE into a very large number of ordinary differential equations, okay? And if you did not mess things too much, and if everything is done properly, then this set of ODEs will inherit the original symmetries of the PDE. For instance, if the original PDE was time reversible, like is the case for Euler equation, then the set of ODEs will be time reversible. Also, if you conserve energy, then the set of ODE will conserve energy. Then, if you put on some statistical physics glasses, you can say, well, this large set of ODE that is time reversible and conserves energy, I can apply to it the standard methods of statistical physics, and for instance, I will get thermalization. So that's basically the idea, and the K-square spectrum that you saw in the previous slide, you understand it very easily by saying that if you thermalize, you have equipartition of energy, and then you have a same amount of energy in each Fourier mode, and because you are in 3D, it makes a K2 spectrum, okay? So that's the general framework. So I've put it here in equations instead of words. So here I have my PDE. I Fourier transform it. So, so I get an equivalent set of equations for the Fourier modes, okay? But now what I do is I impose a Galerkin truncation, okay? And doing that, I get a finite dimensional system. This is a good approximation of the original system as long as the Fourier modes are decreasing rapidly enough with wave number that this truncation is an approximation. So that means dynamics is not influenced by the cutoff. However, the system has inherited some of the conservation laws, and therefore I can forget about convergence to the original ODE, but just look at statistical solution, and there will be solutions that are given by the associated Liouville equation, and the stationary solutions will be given by some kind of Gibbsian distribution with a conserved quantity, and this is what people call in this framework absolute equilibrium. Okay, so what do this system have in general? Well, in general, you will see they relax towards the thermodynamic equilibrium. However, they do that in an interesting way. That is, they start by thermalizing the smallest scales, which are the most rapid. And while doing this, so the system is only partially thermalized. And it's interesting because the thermalized modes, which are in general the highest lying modes, they give rise to an effective dissipation to the large scales. So let me give you now an example. Truncated Euler equation. So this is the Euler partial differential equation in 3D. I do it in Fourier space, periodic solutions. So I get this equivalent system, okay? This is absolutely standard in fluid mechanics. It's a way to write it. The pressure terms are taken care into this projector operator. And the truncated Euler equation conserves both the energy and the helicity. The energy is the square of the integral of the square of the velocity, and the helicity is the velocity times the rotation of the velocity. This has an interesting point, this helicity conservation, that it was discovered only in the 60s when the Euler equation was in 200 years of existence. And so I can write these quantities in Fourier space, and they are exactly conserved by the truncated dynamics. So what are the absolute equilibrium? Well, this was done by Bob Krishnan in the 70s. So in this case, because both energy and helicity are quadratic in the velocity field, the Gibbsian distribution is a Gaussian distribution, so you can compute absolutely everything by hand, and you get that the equilibrium energy spectrum is like this, and helicity spectrum is like this. So basically K squared and K4, plus some correction. So in the case I'm going to present now, this correction term is very small, so it's really K squared and K4. So here is now a numerical simulation. I start with two modes, okay, which in some sense have a maximum helicity. So for those of you who know what it means, this is the so-called ABC flow. So when this is the initial data, and the energy spectrum and the helicity spectrum in blue and red respectively. So let us start the computation. So this regime here is a regime where the PDE, the original PDE was valid, and we have an approximate solution. So it has peopled the modes of higher wave number. And here, at this time, you start that the truncation starts being felt by the system. So then we are not a PDE anymore. Now, you do see now that these higher lying modes, they have started to thermalize. The other modes have not, but those have thermalized, which is something that happens all the time in physics, that the fast degrees of freedom thermalize before. And when you go on, you see a slow relaxation toward the absolute equilibrium, with all those, the thermalized zone extending. So let's do it again so that you see the behavior. Okay? So that's typical of a truncated time reversible system. All right? Now, so let's recap some basic facts. So we it does relax towards the absolute equilibrium. However, it's a very interesting transient dynamics because in some sense, the small scales act like something like, I would say, thermalized degrees of freedom that give an effective dissipation to the system. Okay, let's now do the same thing for the Burger's equation. So now we are in 1D. This is the Burger's equation, the Inviscid Burger's equation written for the velocity u. So I play the same game, Fourier expand, truncate, and then I get a system. This system, as you can see here, I've written it here. It's, you can check explicitly that although you have applied the truncation, then the energy is exactly conserved. This you can understand easily. This, for some people, is not very intuitive. Some people think intuitively that if you do a truncation, you're going to lose energy. But remember, energy is u squared, okay? And the original equation gives you dtu. So the derivative of the energy, you have to sum terms like u dtu, which is dtu squared over 2, okay? And when you sum u dtu, the sum still makes 0 if you impose for k larger than k max that u and dtu are 0. This is because without imposition, dtu would not be 0, but it would be multiplied by a u that is 0, so you don't spoil energy conservation by imposing it to keep it down, okay? So here you have a simulation of the truncated dynamics. So here you see it in physical space. Here you see it in spectral space. It starts from this initial data. And here is a spatio-temporal representation. Let me say that there is an interesting thing in this problem that our friend Samriddhi here has studied some time ago, which is the so-called tigers, which are, you see here, in viscous burgers, you get a shock here. But if you see what happens in the opposite of the shock, you have a structure that happens here. And let's say it's very interesting to study. Especially here, I've given you a higher resolution situation. So this is somewhat before the shock. That is right at the shock, and here is the original tiger coming in. But let's wait a long time, and it will eventually thermalize. Okay? So now I go to the main part of my talk, which is the system I want to study. And from now on, I will always be talking around the equilibrium solution. So here is the Burger's equation when I add a viscous and a forcing term, okay? By the way, if you use this, you've seen that many times, you get it into this form that is perhaps more familiar. So anyway, the system I'm going to be interested to is the one where I put a forcing, which is a Gaussian white noise, both white in space and time, all right? Now, when you take this Gaussian white noise, you can check that. First of all, the absolute equilibrium of the original truncated system without forcing or dissipation, this absolute equilibrium, remember it was flat for the velocity spectrum, was flat in Fourier. So that means that the equilibrium probability is a white noise in space for the velocity. So it's a Brownian for the integral of the velocity. And it turns out that, sorry, I go back here. It turns out that with this forcing, okay, I get, and this dissipation, the very same equilibrium probability is okay. Now, the reason for that, first of all, what is the reason that it's the absolute equilibrium? Well, that's the thing I gave you. You say it's well approximated by the canonical distribution, and the canonical distribution will be equipartition. Equipartition will be a flat spectrum, therefore it will be a white noise. And now the other one, why is it the same? It's because, well, let us check that the same distribution will work. First of all, if I forget about the term in the Fokker-Planck equation coming from the nonlinear term, let's just forget about it. Then I get an equilibrium between forcing and dissipation, linear equilibrium, and that's the so-called Edwards-Wilkinson thing. And it gives also a flat spectrum because the k-square coming from the dissipation is equilibrated by the k-square in the diffusion term of the Fokker-Planck equation coming from the dxf term. So these two terms equilibrate with the Gaussian distribution. And now, so these two terms cancel. And now the nonlinear term, if I restore it, it's just alone, it would be zero in the Liouville equation for the original term. So the whole thing, it's easy to check that it's solution. So what happens is that whatever the forcing I put, I always have the same stationary state. So I'm not going to look at stationary states because they will be the same for everybody, but the dynamics around the thermodynamic equilibrium will be different. And these dynamics I characterize by the time correlation function, okay? So that's the idea. So how many parameters do I have in my system? So I have this equation, this forcing, and here is the conserved energy, which I can write in terms of URMS, okay? So the intensity of the forcing here, if I fix my viscosity, if I change that, all I will change is the URMS, or the energy of the stationary state. So I fix a C so that URMS has a given value, okay? And then if you look at this, viscosity is an extra parameter, okay? So once I fix URMS, I just have a viscosity to fix, okay? Now I'm going to show you numerical results, okay? So to obtain these numerical results, I've used standard pseudospectral methods. For those of you who are technically inclined, you need to perform de-aliasing at Kmax, at two sort of Kmax, or n/3, in order that the usual thing that convolutions can be computed as a product in space works and makes Galerkin convolution. So this is done. And then, as I will take the singular limit where nu goes to 0, and if nu is 0, the noise is also 0, and I recover my truncated burgers, I want in this limit to have a very good energy conservation due to time stepping error. So I set up a fourth order Runge-Kutta for the time step. And of course, this for the force system has no sense because of the white noise, but I still keep it to have something uniform. And the white noise is added separately as a Gaussian thing with a Gaussian variable with value given by square root of dt, etc., as usual. Okay, and all computations are performed with a periodicity length scale of 2 pi. So URMS only fixes a time scale. So in the numerical computation, I set it to 1. And now if you think of it, the systems I'm going to show you, there is only two things to change, okay? One thing is the resolution, of course. I can increase the Kmax, the resolution. And the other thing is the viscosity. Now, this viscosity, being of a fluid dynamical origin, I like to think of it as a Reynolds number, so I will introduce a Reynolds number that is URMS of a new Kmax. It's the Reynolds number at the highest scale, okay? And so in that case, the truncated Inviscid Burgers result is obtained in the limit Reynolds goes to infinity, nu to 0. So now what do we expect, okay? So I'm going to spend 2 minutes to say what to expect. Small Reynolds number. Remember, the Reynolds number is at the maximum wave number. So if the Reynolds number is small there, it's going to be small all over the place. So at small Reynolds number, no, sorry. It's going to be small in a region around that. So in this place, you expect the linear scaling Edward-Wilkinson. And then the correlation time scales as 1 over nu k squared, that's at k minus 2. Now, I don't need to go on at length, given the audience, that at higher Reynolds number, you expect the KPZ scaling, which in that case for the correlation function would be 1 over k to the 3/2, okay? And the new point I will spend the next transparency to explain before I show you the actual result is that at infinite Reynolds number, in the truncated Inviscid Burger case, you expect 1 over URMS k. Now, so it's 3 different scalings, -2, -1.5, 1, and the question I want to answer is why in the Inviscid case do you expect that? So there is a simple analytical solution, analytical computation that leads you to understand why you expect that value. The idea is that you can compute the second time derivative of the correlation function, okay? Now, because of time invariance, what you can do is you can, instead of having 2 derivatives acting outside, you can integrate by part 1, and then you get a dt on the first and a dt on the second. When you get a dt on the first and a dt on the second, you can use the equation of motion, which is quadratic, and so you get a fourth order term, and that you can compute. It's a one-loop diagram. And when you do the computation, you find this scaling, which is like 1 over k, okay? So now I go to my main results. Okay, so I did some time ago in Bangalore a list of runs, and let's forget about those that I use only to interpolate. So you see, the only thing you're interested in is this column, and this is the viscosity. This is new here. So the 3 main runs, one is at 0, and this will give something, the k minus 1. One is at 0.03 for this run, which are done at 1,000 cube, okay? So this one will give KPZ. And in one run, I doubled the viscosity so that I have a small amount of Edward-Wilkinson scaling to show. And all the other runs are just interpolation. Now let me just tell you that the way this is computed is that we have a very large number of realization of the equation, which is one of the columns here, which is, I guess, and here. So it's 128, but then each one of them is integrated in time, and you compute the correlation function on the fly, or you compute also the, how do you call, well, those are technical details. So you manage to compute the correlation function, and then you output it. So let me show you the results. Sorry? Yes, it's automatically switched off because as I fix URMS, the forcing is proportional to the viscosity in order to keep. So and I forgot to say, I set up the initial data as the equilibrium, so I don't have to lose time to converge to the equilibrium. So here are the results. So let's say, so first look at this one where you have only the 3 runs I was talking about. So the one with the highest, largest viscosity has a little bit of Edward-Wilkinson here. By the way, this is wave number, and this is correlation time, and it's log-log. So here you see, and the 3 lines, black lines, are k minus 2, k minus 1.1, 1.5, and k minus 1, okay? So the one on the bottom here, you see a little bit of k minus 2 at the highest wave number, and then it switches to the k minus 1.5. The one that has Reynolds number 1 of order 1 at the highest wave number, the one that has the Reynolds number 1 at the highest wave number goes to 1.5 all the way. And the one that is at nu equals 0 goes to minus 1 all the way, okay? Now, here is, you have all the interpolation where every time I have divided the viscosity by 2 every step, okay? So those are the bunch of runs. Now you see the same ones on the right, compensated here by k, so that the Inviscid scaling is horizontal, and here compensated by k to the 3/2, so that the KPZ scaling is horizontal. So you can see the crossover behavior here. And okay, let me now, what I've shown you here, I should have said it from the beginning. So again, if you have very good eyes, you can read tau 1/2. So what I've computed is the value of the time at which the correlation function has decreased by 1/2. Okay? So now let me show you the correlation functions, how they look like. So here you have the graphs you've seen before. Here you have the various correlation function in the KPZ regime. So here you have, I've multiplied tau by k, so they don't collapse. And here I've multiplied tau by k to the 3/2, and they perfectly collapse. So you see a very good KPZ scaling here, okay? Let me mention something extra here, is that as expected, if you zoom over here, which I cannot show here, but there is a cusp on the top of the correlation function. This is due to the effect of the white noise. That is, the second derivative on the top is not at all well defined. Now I show you the equivalent one for the Inviscid Burger scaling. So now a big difference. If you zoom on the thing here, you will see that there is a well-defined parabola on the top with second order thing. And now if you collapse according to KPZ, it doesn't collapse anymore. And if you collapse according to K minus 1, it does collapse, and you actually see the parabola. So what this thing shows you here is that the whole correlation function, at least up to T 1/2, which is obtained when I get here to 0.5, so this is the position of T 1/2. So you see the scaling of the whole correlation function is the same as the scaling of the parabola on top, and my analytical computation was about the parabola on top. Okay, so that you could see the crossover, I've blown up one of these things. So again, this is the lowest Reynolds number, so I have a bit of Edward Wilkinson here, and then it goes into KPZ, okay? This is the one where Reynolds number is over the 1 here, so I'm KPZ all the way. And now when I start decreasing the viscosity by factors of 2, it does this. So you see the highest wave number go faster into the K minus 1 regime, but if you look now at the lower wave number, they also go for finally, of course, when it's a 0, it's K minus 1 all the way. All right, so now I'm about to do my conclusions. So we've explored the force and dissipative truncated Burger's equation at thermal equilibrium in the Inviscid limit. We looked at the scaling of the correlation time, and we found 3 scalings with the wave number which are different and that are found when you increase the Reynolds number. So at very small Reynolds number minus 2, you increase, you get into KPZ, and you increase even more, and you finally get into this Inviscid regime. So I will end up by asking a question, which is there a new unstable fixed point for the -1 scaling? Of course, this is the linear fixed point, and this is the KPZ fixed point. Question, is there a fixed point for that? And if so, what is the appropriate renormalization group? And I will finish by just mentioning that this -1 scaling is ubiquitous in the large scales of, in the fluctuation of large scales turbulence. You can even find it in Navier-Stokes when it's a force at a small scale. You find it in truncated Euler, truncated Gross-Pitilevsky, etc. So this is the end, and I again thank the organizers.